Today we're going to talk about something called an improper integral. We need to explain what an improper integral actually is, but before we do that, let's see why it might come up, and then define an improper integral when it seems appropriate. So we're going to start by recalling the fundamental theorem of calculus. If f is a continuous function on an interval ab, a closed interval ab, then 1, f has an antiderivative that is valid on that interval, and 2, we can evaluate the definite integral of little f of x dx from a to b on that interval, that is, by looking at the net change of the antiderivative there. So this leads to a natural question. And that natural question is, what if f is not continuous? On this interval? What if there's a point of discontinuity? Well, the answer depends on what type of discontinuity you have. So if f has a jump discontinuity, that's supposed to be an m, jump discontinuity. Let's say let's call it c. At c, in this interval from a to b, then we can integrate from a to b f of x dx by just splitting it apart into two separate integrals, from a to c plus the integral from c to b. Now remember what a jump discontinuity is. A jump discontinuity means that the left and right limits both exist, but they're just not equal to each other. So the idea is that you have some function, so let's say this is our x-axis, and you have some function which is continuous, say, everywhere except for at this point c. And then we have some jump. So let's put an a over here and b over here. So the idea with a jump discontinuity is that, again, the limit from the left exists, the limit from the right exists, but those limits are not equal to each other. So this is a jump discontinuity. If you want to integrate from a to b, from here, from a to b, you can do that by simply integrating from a to c first, and then adding another integral in from c to b. So you do each one separately, and that's fine. So if you have a jump discontinuity, it's very easy to get around that, because now you can use the fundamental theorem here. So you can use the fundamental theorem on the interval from a to c, and then you use the fundamental theorem separately on the interval from c to b. So you can still use the fundamental theorem of calculus, but you just have to do it twice. And then you add the two definite integrals together. Okay, so that's what to do with if you have a jump discontinuity. But what do you do with an infinite discontinuity? What to do with an infinite discontinuity? So if you have an infinite discontinuity, that means basically you're dividing by 0. For example, you have perhaps some vertical asymptote. So you have something that looks maybe like this. So you have something, so maybe this is C, and this is A, and this is B. So suppose you have something that looks like this, where you have a vertical asymptote at C. So this curve, let's say, is going up like this. This curve is going up like that. So you have some vertical asymptote there. Let me just get rid of these other lines. Something that looks like that. So what about this? Vertical asymptote at x equals c. What do you do in a case like this? Let's break it down into different cases. So case 1, suppose that your function is continuous on an interval from a to c, not including c, but has a discontinuity, an infinite discontinuity at x equals c. So in this picture, or in this case, let's draw a picture. You're looking at the left side of what we have over there. So you have c here. Let's say it's going up like that. So this is the left side of our picture above. So you're continuous on the interval from a to c, but not including c. So that's why we have a bracket for a, because we're including a, but we have a parentheses for c, because we're not including c. It's continuous from a to c, but not including c. So what do you do in a case like this? So here's the idea. Pick some number, let's call it t. So pick some number t close to c, but to the left of c. So in our picture, we want to pick some number close to c, but to the left of c. So let's say right here. There's a number that's close to c and to the left of c. Now, note, f is continuous on the interval from a to t. So that means we can use the fundamental theorem of calculus to compute the definite integral from a to t. So the integral from a to t of f of x dx is equal to the antiderivative evaluated at t minus the antiderivative evaluated at a. So in terms of our picture, that's going to give us the area underneath the curve between a and t. Our function is continuous from a to t, so that means we can use the fundamental theorem of calculus there. Now this isn't going to give us the same thing as the definite integral from a to c, but the idea is that if t is close to c, then this integral from a to t of f of x dx is an approximation to the integral from a to c f of x dx. And the closer that, so if you pick a t that's closer, say over here, then you're going to get an even better approximation. So the closer t is to c, the better the approximation becomes. So what do we normally do when we have a situation like this, where we get a better and better approximation as t gets closer and closer to c? Well, we take a limit. So we define the integral from a to c of f of x dx to be equal to the limit as t approaches c of the integral from a to t f of x dx. Now t is necessarily smaller than c, it's to the left. So t has to approach c from below. So we put a little minus there. Remember when you see t approaching c to the minus sign, what that means is t is equal to c minus something. T is c minus something. So t is to the left of c. So this is a limit where t approaches c from the left. And we do that because t has to be smaller. If we picked a t that was bigger than c, then we'd be jumping over our point of discontinuity. Let me just try to improve my curve here. So if we picked a t which was bigger than c, we'd jump over this point of discontinuity and we couldn't use the fundamental theorem of calculus anymore. So what that means is that we're not going to pick a t over here. Instead, we're just going to pick a t to the left. And then you compute the limit as t approaches c from the left or from below. So t approaches from the left. So note, let me just write this down. If t was bigger than c, then we could not use the fundamental theorem of calculus because f is not continuous on the interval from a to t if t is bigger than c. Okay, so that's why we have to approach it from below. Let's look at an example. Let's just start a new page here. Example. Let's compute the integral from 2 to 4 of 1 over the square root, let me try that again, square root of 4 minus x dx. 1 over the square root of 4 minus x. So if you were to graph this, it would look kind of like the picture that we already drew. Let me just move this y-axis over a little bit, like that. Well, that's a little too far. Let's try that again. Let's leave it over there. And we'll draw our x-axis here. And we don't really need the y-axis for this. But if we graph this, so let's say that this is 1, 2, 3, 4, like so, then this looks like the graph has, it has a vertical asymptote here at 4, and then it looks like this. Something like that. So it looks very similar to the picture that we have in mind. So we want to integrate from 2 to 4. So let's draw a line right here. So we want to integrate from 2 to 4. We have an infinite discontinuity. At x equals 4. So what we're going to do is we're going to pick some t value that's close to 4, but to the left of it. And we're going to integrate from 2 to t. And that's going to give us the area underneath the curve between 2 and t. So this is something we can compute. Let me just fill it in so that way we have some nice colorful region that we can talk about. There we are. So t is less than 4. T is less than 4. So our function, so this is y equals 1 over the square root of 4 minus x. Notice if x is bigger than 4, this thing is undefined because we have the square root of a negative number. So we need x to be smaller than 4. So that's why we're integrating from 2 to 4. So we have an infinite discontinuity at x equals 4. So we want to integrate from 2 to t 1 over the square root of 4 minus x dx. All right, so how are we going to do this? Well, the first thing to realize is that this is actually a substitution. We're going to let u be equal to 4 minus x, and then du is equal to minus 1 dx. Let's just look at this it is an improper integral. Let's look at the indefinite integral first. 4 minus x dx. Let's find an antiderivative. So this is the integral of 4 minus x to the minus 1/2 dx. So you can see that this is a composition, and the inside function is 4 minus x. So this is going to be our u, and du is negative dx. So that means that this is negative du. So we have the integral of u to the minus 1/2, and then it's a negative du. So let's put the negative outside, du like that. So it's minus, now it's u, we add 1 to the exponent, and then we divide by that new exponent. Minus 1/2 plus 1 is a positive 1/2. Plus c. So this is equal to minus 2 times the square root of u plus a constant. That's the indefinite integral. So if we want to compute the integral from 2 to t, which is a definite integral of 1 over the square root of 4 minus x dx, this is equal to, well, don't forget to plug in what u is. U is equal to 4 minus x. So this is minus 2 times the square root of 4 minus x plus c, but we don't need that. We're doing a definite integral, so any antiderivative will do. So this is going to be 2 to t. This is minus 2 square root 4 minus x plus a constant. Okay, let me just give myself a little bit more room here. There we are. So if we evaluate this, we're going to have minus 2 times the square root of 4 minus t minus a minus 2 times the square root of 4 minus 2. So that's minus 2 times the square root of 4 minus t plus 2 square roots of 2. Now that's the area of the shaded region between 2 and t. What's the area of this region? Notice that it depends on t. If I choose a different t, I'm going to get a different area. If I choose t close to 2, I'm going to get a smaller area. If I choose t closer to 4, I'm going to get more area. So the area here definitely depends on this t. Well, what happens as t gets close to 4? So the limit as t gets close to 4 from below of this quantity, 1 over the square root, the definite integral from 2 to t of 1 over the square root of 4 minus x dx is the limit as t goes to 4 from below of this quantity, minus 2 square root of 4 minus t plus 2 square roots of 2. T is getting close to 4, so that means that this quantity right here is getting close to 4. So that means the limit is equal to minus 2 times the square root of 4 minus 4 plus 2 square roots of 2. There's no t there, so that doesn't change. But 4 minus 4 is 0. So that means you have minus 2 times 0 plus 2 square roots of 2. So the answer is 2 square roots of 2. So to summarize, the integral from 2 to 4 of 1 over the square root of 4 minus x dx is equal to the limit as t approaches 4 from below of the integral from 2 to t of 1 over the square root of 4 minus x dx. But this quantity is going to, this limit right here, we're computing the limit of this, is 2 square roots of 2. So that means the area underneath the curve is 2 square roots of 2, which is kind of a remarkable thing, because if you look at this region, it's unbounded as you move to the right. The curve is going off towards infinity. So there's a gap here, but despite that fact, you still get a finite area. That's because the gap is so small. So there we have an example of computing what we call an improper integral. The integral is improper because it's not a definite integral. It's not definite because of the discontinuity. If this function were continuous at 4, then this would just be a definite integral. But since there's this infinite discontinuity, it's what we call an improper integral. So that is our first case. That is the first case that we've seen. Case 2 is similar. So for case 2, suppose that your function, let's just write it this way, our function is continuous on the interval from c to b, including b, but not at c. So this is sort of the mirror image of what we were looking at before. So we're going to have something that looks like, well, I don't need a y-axis, so let's just draw in our x-axis. And we're going to draw in a vertical asymptote here at C. And here's B. So this is basically the mirror image of what we saw before. So we have this infinite discontinuity at C. So in this case, you're going to do basically the same thing. The idea is you want to compute the integral from C to B, f of x dx, but you can't use the fundamental theorem of calculus here because you have this infinite discontinuity. So instead what you do is you pick some number, let's call it s this time. You pick some number s, pick s close to c, but in this case to the right of c. And that's going to give you the area again underneath the curve between s and b. It's only area underneath the curve because our function is always above the x-axis. Our function doesn't need to be above the x-axis for this to be true, for this method to work. We can look at an example in a moment, and we'll pick an example where the function is negative. But if your function is positive, then it gives you the area under the curve. So what you're going to do is you're going to first compute the area from c to b, f of x dx. Not c, that's what you're trying to compute, s. You're going to compute the integral from s to b, and that's going to give you this region right here. And then you compute the limit as s goes to c from above. So in this case, s is getting close to c, but it's bigger. So s approaches c from above. That means s is equal to c plus something. So s is bigger. S is approaching from above or from the right. And that's how you compute an improper integral of this type. So let's look at an example. Let's look at the integral from 0 to 1 of ln of x dx. This is an interesting example because here the function is negative on this region. So it's going to look something like this. So this is y equals ln of x. This spot right here is 1. So what we're interested in is we're interested in the area above the curve. Now this is a definite integral, so we're going to get a negative answer. Remember, if a definite integral has an integrand which is negative, then it doesn't give you area, it gives you the opposite of the area. So this is going to be some negative value. So we're looking at this area right here, or this region. But like I say, it's not going to be area, it's going to give you the opposite of the area. So what we're going to do is we're going to pick an s we're going to pick an s which is bigger than 0. And then we're going to compute the definite integral from s to 1. So this is going to be equal to the limit as s goes to 0 from above of the integral from s to 1, ln of x dx. Between s and 1, our function is continuous. So this I can compute using the fundamental theorem of calculus. And then I just compute the limit as s goes to 0. So of course 0 is right here. So s is approaching 0, but it's bigger. It's necessarily bigger. I can't pick an s here because then I've got this infinite discontinuity to worry about. So I don't pick an s to the left. It's just above. It's just bigger. It's to the right. So s is approaching from the right. So let's compute this definite integral. Well, in order to do that, we need to remind ourselves what the antiderivative of ln of x is. Now you may remember, but if not, let's just compute it. So let's find an antiderivative of ln of x. And I say find because it might be underneath the carpet somewhere. So actually we're going to look at this indefinite integral, ln of x dx. So the way to evaluate this integral is using integration by parts. You let u be equal to ln of x, and then dv is equal to dx. So du is the derivative of ln of x, 1 over x dx, and then v is the antiderivative of 1. So that's going to be x. That's an antiderivative. So we have the integral of ln of x dx is going to be uv minus the integral of v du. So this is ln of x times x minus the integral of v, which is x, times du, which is 1 over x dx. So x times 1 over x is 1. So this is equal to x ln of x minus the integral of 1 dx, but that's just going to give us an x. So we're going to have x ln of x minus x plus a constant. That's our general antiderivative. We only need an antiderivative. So we'll pick x ln of x minus x. So we're going to just plug that into this thing right here. Let's rewrite it. The integral from 0 to 1 ln of x dx is equal to the limit as s goes to 0 from the positive side, the integral of s1 ln of x dx. But now we have an antiderivative. Remember, ln of x is continuous between s and 1. It's continuous between s and 1, so we can use the fundamental theorem of calculus. So this is the limit as s goes to 0 from the positive side of x ln of x minus x, and then we're going to evaluate this between s and 1, like so. So this is the limit as s approaches 0 from the positive side. We plug in 1, so we're going to have 1 times ln of 1 minus 1. That's the first one. And then minus, we plug in s for x. So it's s ln of s minus s, like so. So ln of 1 is 0. So we have the limit as s approaches 0 from the positive side, minus 1 minus s ln of s, minus a minus is plus s. S is going to 0. What about this term right here? Well, that's actually going to go to 0 as well. The easiest way to see that is to probably use L'Hopital's rule. The limit as s is approaching 0 from the positive side, s ln of s, you might want to rewrite that. This is an improper form, an indeterminate form, because s goes to 0, but ln of s is going to negative infinity. So this is of the type 0 times negative infinity. So that's an indeterminate form. But you might want to write it like this, ln of s divided by 1 over s. And now we can use L'Hopital's rule. Right, this is the limit as s goes to 0 of the derivative of the top is 1 over s, the derivative of the bottom is minus 1 over s squared. So this is L'Hopital rule. And This, of course, simplifies. That's minus s. So you're looking at the limit as s goes to 0 from the positive side of minus s, which of course is 0. So that's why both of these terms go to 0. So what are you left with? The integral from 0 to 1 ln of x dx is equal to minus 1. Let's just move that right up here, and then we'll just put a little circle around it. So that means the integral, let's go back and look at our picture. So that means that the region, if you integrate from 0 to 1, you're going to get negative 1. So that means the area here between 0 and 1, as s goes to 0 from the right, the area is 1. But this is a definite integral. The function is negative, so you don't get area, you get the opposite of the area. So the area is 1, but the result is negative 1. So that's an example of an improper integral where you have a discontinuity at the left endpoint. Now, in both of these examples we've looked at, we've ended up with finite answers. So in our first example, we ended up with a finite area underneath the curve of 2 times the square root of 2. And here, for this example, we found that the area was 1, so the definite integral was the opposite of that, which is minus 1. Sometimes you won't get a finite answer. Let's look at another example. Let's look at the integral from 0 to 3, 1 over x squared dx. Now this has an infinite discontinuity at 0. So that's on the left side. So it's going to look something like this. So this is y equals 1 over x squared. And we're integrating from 0 to, let's say, 1, 2, 3. Let's say that that's 3 right there. And in this case, our function is positive, so we're trying to find the area underneath the curve. In this case, the answer won't be finite, though. So we approach it in the same way as before. You pick some number, let's call it s, which is bigger than 0, like that. And so we're going to find the area between s and 3. This is necessarily finite. It's finite because we bounded it. You can see that it's finite. The function is continuous between s and 3. It's only at 0. It's at 0 that we have a problem. So between s and 3, it's fine. It will have a finite area under the curve. So this is going to be equal to the limit as s goes to 0 from above, from the right, the integral of s to 3, and let's write this as x to the negative 2 dx. I've written it as x to the negative 2 so you can see that it's x to a power. So that means we can use the power rule. So it's the limit as s goes to 0 from the positive side. So x is x to the negative 2. You increase the exponent by 1, and then you divide by that exponent from s to 3. So this is the limit as s goes to 0 from the positive side. This is minus 1 over x between s and 3. So this thing we can compute in terms of s. Limit as s goes to 0 from the positive side, so this is minus 1 over 3 minus a minus 1 over s. But as s goes to 0, 1 over s goes to infinity. So this thing is infinity minus 1/3, which is infinite. So that means the area under the curve is infinite. If the limit is infinite, or if the limit doesn't exist, we say that the improper integral diverges. Let's write that down. If the limit does not exist, which includes being infinite, or is infinite. If the limit is infinite, it doesn't exist, so that's a special case of not existing. So if the limit does not exist, or is infinite, which is a special case of does not exist, we say the improper integral converges. diverges rather. Sorry, if it doesn't exist, you say that it diverges. Diverges. So in this case, in example 3, the improper integral diverges. If the limit does exist, we say the improper integral converges. This is terminology that we get from limits to begin with. If a limit doesn't exist, it diverges. If a limit does exist, it converges. So we're just now applying that to these improper integrals. So if the limit does not exist, we say the improper integral diverges. And if the limit does exist, we say the improper integral converges. So in this example, so in our examples, so our first one was the integral, let's just go back. Our first one was the integral from 4 to 2, this one right here. The integral from 2 to 4, rather. The integral from 2 to 4, 1 over the square root of 4 minus x dx. This one converges because it's equal to 2 square roots of 2. The integral from 0 to 1 of ln of x dx, that one converges. So the first one is equal to 2 square roots of 2. This one is equal to negative 1. And the integral from 0 to 3 of 1 over x squared dx, this one diverges. This is the one that we just computed because it's equal to infinity. So that one diverges. We have a theorem which is quite useful, and you can compute this directly. It says that if b is greater than 0, then the integral from 0 to b of 1 over x to the p dx. Well, what are we going to say about this? Well, we just did an example like this. So this example that we just did, b is equal to 3, which is greater than 0, and in this case, p is equal to 2. So what happens to be true is that if p is bigger than 1, it's going to diverge. So this will diverge if p is bigger than 1, and it will converge if p is less than 1. That's related to the first example that we did, where in this case you could say that p is equal to 1/2, and so it's related to that. So the natural question is, what happens at 1? Well, it diverges at 1 as well, and you can easily show that. Example. The integral from 0 to b of 1 over x dx is equal to the limit as s goes to 0 from the positive side, the integral from s to b, 1 over x dx, and this is equal to the limit as s approaches 0 from above. And now we want to find an antiderivative of 1 over x, which we know, ln of x, from s to b. So this is the limit as s goes to 0 from the positive side, ln of b minus ln of s. Now this quantity, ln of s, this thing is going to go to negative infinity as s goes to 0. I mean, you can look at that right here. We have the graph. So this is ln of whatever, and as you go to 0, it's dropping away. It's dropping away to negative infinity. So this limit right here is negative infinity. Ln of b is just some constant, minus a minus infinity, so you're going to end up with positive infinity. So this one diverges. So far we've talked about what to do if you have a discontinuity at the left endpoint and the right endpoint, but what happens if it's in the middle? That's also a possibility. So let's call that case 3. Case 3. In this case, your function is continuous at or on the interval from AB. Let me rewrite that. So it's continuous at all points in the interval from A to B except one. Let's say except C, which is between, which is inside the interval. So it's continuous at all points in AB except C, which is not A or B. So that is A is strictly less than C is strictly less than B. So an example of that would be something that looked like this. Something like that. So let's say that this is y equals f of x. And let's say that this is A, and this is B, and C is right in the middle. Or between. It just has to be between. So in a case like this, so in this case, write the integral from A to B of f of x dx is equal to the integral from A to C f of x dx plus the integral from C to B f of x dx. And then do each one of these separately. So do each separately. Okay. If either one of these diverges, then they both diverge. Well, then the sum diverges. That's what I meant to say. So if either one diverges, then the integral from A to B f of x dx diverges. So if you have an infinite discontinuity in the middle, then you split it up like this. You look at the improper integral from A to C and the improper integral from C to B. These are both improper integrals. So these are both improper integrals. Just want to change the style to blue. So the idea is if you start with an improper integral where the infinite discontinuity is in the middle, you divide it up into two improper integrals. Notice that the discontinuity is on the right endpoint here, but the left endpoint here. And so then you use case 1 and case 2 separately. So you do each separately. And if either one of these diverges, or both of them, if either one diverges, or both, then the original thing diverges. So if we look at an example, let's say the integral from -5 to 3 of 1 over x squared dx. So in this case, we would write this as the integral from -5 to 0, 1 over x squared dx, plus the integral from 0 to 3, 1 over x squared dx. Let me just fix the 1 there. We've looked at this example before. So this thing looks like, if we draw our x and y axes here, that's x, that's y, we have an infinite discontinuity at 0. It looks like this. So 1, 2, 3, 4, 5, here's -5, and 1, 2, 3, here's 3. So we're looking at the improper integral from -5 to 3. It's improper because we have that infinite discontinuity in the middle. Now we already know that this one diverges. So we saw already this diverges. So I don't even have to compute the one on the left. So the consequence or the result then is the integral from -5 to 3, 1 over x squared dx diverges. If either one of these diverges, then the sum diverges. That's all there is to it. We don't even have to check the other one.